Hello all. In this video I'm going to talk about simulated annealing as an alternative approach to hill climbing. It's a variation on hill climbing, but it has some really interesting properties that I'll talk about here in just a second. Let me bring up my notes. So simulated annealing does a couple of things. It limits the number of neighbors, so you don't necessarily look at all the neighbors. It allows the algorithm to move explicitly to neighbors that are worse than the current state. So it does allow the algorithm to go downhill. And it incorporates randomness as mediated by a value we call temperature. And so I'll talk about this a little bit. So annealing itself. So this is simulated annealing. So what the heck are we simulating? Annealing is a process that's used in metallurgy where you follow a certain schedule of heating and cooling the metal to get certain effects in the final metal product. That's pretty much the limit of my understanding of metalworking. But it has this sense that there's a schedule of temperature changes that is helpful. So with simulated annealing, what we do most of the time is we set a schedule where our temperature is high initially and then gradually decreases over the run on a schedule, not necessarily impacted by what's going on in the particular search, but just over a certain number of steps, the temperature declines. What does that do? Well, when the temperature is very high, it increases the probability that we'll take one of those downhill steps. And as the temperature decreases, the probability that we'll take a downhill step also decreases. So we fundamentally just don't all, it starts off making a lot of random moves initially, and then hopefully as we have found a very promising region of the state space, the randomness diminishes and allows us to do more of a straight hill climbing kind of search. So I have some rough pseudocode here. This may be all that I look at. I do have pseudocode written in the style of the hill climbing algorithms we were looking at before in the earlier video, but I don't know that we need to look at this one that closely. So we'll see how it goes. All right, so much like hill climbing, we start by setting the current state to some initial value, and we compute its objective function value. And then we set up the initial temperature and the schedule for changing it, which is a parameter you can change in this algorithm. And then we have our loop very much like the while loop that we have in hill climbing. But notice that this is more like the simple hill climbing. We're generating one neighbor at a time, stochastic simple hill climbing, because we are generating a neighbor at random and we're computing its value. So the way that simulated annealing usually works is if you generate a neighbor that is better than your current state, you just always take it. So if you find a neighbor that would take you uphill, you don't worry about randomness. You just go uphill. So if the value of the new random neighbor is a bit greater, then it becomes our current state. Where things get different is what we do if it's not better. So with the other algorithm, with the hill climbing algorithms, we just keep looking at more children. Here, we're going to decide whether maybe we're going to take that neighbor anyway. So we calculate the difference in the quality between the current neighbor and the current state and its neighbor. So delta E is just the difference in the objective function values for those two states. And then we generate a random number between 0 and 1, and we compute a threshold. E raised to the power of negative delta E divided by T. Fundamentally, as T gets larger, this probability, this is our threshold, it's going to get lower. So our random number we generated between 0 and 1 will have to be larger in order to actually trigger It has to be smaller than this boundary in order to trigger the change. So if we have a very small number and this is a very large threshold, we are likely to take this not so good neighbor anyway. All right. That's the idea of simulated annealing. It has some really nice properties as a variation on hill climbing, and it's a good example of the ways that you can stretch the algorithm to make it work in a slightly different way. I have seen variations on simulated annealing that have done things like compute the t value based on what quality of neighbors you've been generating. So as we're generating the neighbors here, we keep track of how the quality is going, and if we're in kind of a bad place, we'll reset t to a higher level. That isn't quite the idea, the metaphor that annealing uses, but it is something that I have seen people do as a variation on this. All right, so that's really the most that we're going to do with simulated annealing for right now. It is something that's easy to implement and easy to test just to see how it works. So if you're curious, I encourage you to go ahead and do that. In the next videos, I'm going to talk about beam search, which is a further step away from hill climbing. It's a very interesting population-based approach to hill climbing. And it has, again, a dozen different variants. And it'll lead us toward genetic algorithms, which are really interesting, and we'll see those in a future video as well. I'll see you soon.